Hi everyone, welcome to the paper presentation for a detailed look at MIMO performance in 60 GHz wireless LANs. My name is Shivang Agarwal, and this was a joint work in collaboration with Shisa and Ajit from the University at Buffalo and Dimitrios from Northeastern University. So the 60 GHz unlicensed frequency band has been touted as the prime candidate technology to enable the next generation of wireless applications. So why is that? So the advantage of being at such a high frequency is that there are large amounts of spectrum available. Around the 60 gigahertz frequency, there is around 14 gigahertz of unlicensed spectrum that are available. This is in comparison to just 600 megahertz of spectrum that's available around the 5 gigahertz band. Now, due to these large amounts of spectrum in the 802.11ad standard, which governs the 60 gigahertz frequency band, each channel is around 2.16 gigahertz wide. And again, to compare to legacy Wi-Fi, each channel only has a maximum channel width of around 160 megahertz. These ultra-wideband channels in turn lead to extremely fast data rates, with the 802.11ad standard promising data rates more than 5 times faster than that of legacy Wi-Fi. Now, in the future, there will be applications that demand even higher throughput, and the AP client density is going to increase year over year. Due to these reasons, we need even higher data rates. Now, a key limitation of 802.11ad is that it only supports communication over a single stream. Now, the 802.11ay standard, which is the successor to the 11ad standard, supports communication over multiple streams, specifically up to 8, via both single user as well as multi-user MIMO, and thus promises data rates of up to 100 gigabits per second. Now, one of the key things that MIMO performance depends on is how well the multiple streams of communications can be separated at the receiver. Now, in sub-6 gigahertz channels, due to the rich scattering, this is fairly a simple task. However, at 60 gigahertz, because the communication is directional, the channels are sparse, and due to the sparsity, the separation of these multiple streams becomes very challenging. Thus, beam selection now becomes critical to MIMO performance. And this, of course, is in addition to user selection, which is already an important task to ensure high MIMO performance, irrespective of the frequency band. So what's the overhead of the beam selection process in MIMO? So let's say we have a fixed user group, and each user in that group has n analog beams, and they want to communicate using m simultaneous data streams. So for single user MIMO, the overhead is of the order of n choose m squared. And for multi-user MIMO, the overhead is of the order of n to the power 2m. This is too high for any practical mobile scenarios. So despite the importance of MIMO and the challenges I just explained to you, experimental evaluation of MIMO performance in 60 GHz is really limited, primarily due to the lack of hardware. Now, the limited recent work that has been performed in this area has performed evaluation in only a single environment, which has typically been a large open space. And this is not representative of real world performance. Hence, performance with different multipath characteristics remains largely unknown. So in this work, we make the following contributions. We conduct the first large-scale experimental evaluation of single-user MIMO and multi-user MIMO in 60 GHz wireless LANs. We explore whether it's possible using simple heuristics to decide when to enable MIMO. We conduct a thorough study of the overhead of beam and user selection for a given link or a given group. And finally, we propose and evaluate heuristics that perform this user and beam selection with low overhead. So to carry out the study, we use the X60 testbed, which is a software-defined radio-based 60 GHz testbed with fully programmable physical and MAC layers that provides gigabit data rates, which are similar to what 11AD provides. It also comes with a user configurable phased antenna array, which can produce 25 different beam patterns, and each of these beam patterns contains side lobes, which are similar to commercial 60 GHz devices. Now, the thing is that X60 doesn't inherently support MIMO. So to perform the study, we do trace-driven MIMO emulation, where we assume that there are multiple RF chains co-located at the AP and or the client. Now, the details of this are in the paper, so please definitely take a look if you're interested. So using this setup and methodology, we collected channel traces in 4 diverse environments. One is a large, long, narrow corridor. Then there is a lab and conference room with different layouts and reflections, and a wide open space, which is the lobby of the building. So now let's move on to the key results that we obtained during this study, starting with the classification and analysis of our users or groups based on the MIMO performance. So here we're just focused on the maximum MIMO performance that can be achieved, ignoring any effects of the beam search overhead. So to begin, we plot a CDF of the MIMO gain across our entire data set. And basically for both single user as well as multi-user MIMO with 2-stream and 3-stream communication. So the key takeaway from here is that if you see in about 80% of cases, the gain for both single user and multi-user MIMO is greater than 1. This means that generally MIMO leads to better performance than if we were using just a single stream to communicate. Further, we classify the links or groups based on how well they're performing. So we classify a link or group as strong if it achieves more than 75% of the optimal multiplexing or MIMO gain. The link or group is satisfactory if the gain is more than 1, and it's weak if the gain is less than 1, which means that actually using MIMO hurts performance. So here we show the percentage of cases that fall into each of these categories for each location for both single user and multi-user MIMO when using 2 streams and 3 streams to communicate. So if you see in the lobby and the lab, most of the links or groups fall under the strong or satisfactory category. On the other hand, for the conference room and corridor, about half of the groups or links, and in some cases even up to 77% of the groups fall under the weak category. So why is that? So let's take a look at the corridor and conference room now. So in the corridor, if you see the layout, the users are positioned back to back from each other. This means that when communicating with the TX, they will have similar strong beam pairs. The interference will be high, and hence the zero forcing penalty is high. In the conference room as well, the user orientation plays a role. So there are users like 4, 5, and 6, which face away from the transmitter, while users 3 and 7, if you see, are at a really wide relative angle with respect to the TX, where even single stream communication becomes challenging. Finally, a general reason that MIMO performs worse, irrespective of the location, is that the AP's TX power must now be split across the multiple streams. This means that at the RX, the received signal will be with a lower power, and hence the MCSs supported will be lower as well. So next, we try to answer the question, can SISO SNR be used as an indicator of MIMO performance? So to answer this question, we plot here on the x-axis the single stream SNR of all our links or groups in single user and multi-user MIMO, and we plot it against the gain that link or group provides when using multi-user MIMO. So if you see for the 2-stream case marked in green, we were able to come up with a threshold that says that above this threshold, if the single stream SNR is above this threshold, then MIMO, the gain will always be greater than 1, and hence MIMO always helps. So we should do MIMO in that case. We can similarly, were able to come up with thresholds for the 3-stream case, and hence the answer is yes, that SISO SNR can be used as an indicator of MIMO performance. But can it be used as a more fine-grained indicator of MIMO performance? So if you see the areas that I've marked with the black circles here, you can see that similar single stream SNRs lead to really a varied MIMO gain. This means that unfortunately you cannot use single stream SNR as a fine-grained indicator of MIMO performance. Now we analyze this in detail in the paper. So again, take a look if you're interested. So next we'll talk about the beam selection overhead. So the beam selection overhead in MIMO, of course, depends on the number of beams that are there in the APs and or the client's code books, and it can be prohibitively large, as we've seen before. So to give you an idea, for our test bed, for the X60 test bed, there are 25 beams at each node, and hence there are 625 beam pairs per AP client pair. Now, we calculated for 3x3 single user MIMO, and the beam selection overhead is roughly half a second while for 3x3 multi-user MIMO, it's more than 22 seconds. And these are, of course, too large. So to reduce this, there are a couple of ways that we can do that. So one, we can have heuristics based on the angular separation of the beams, and the other based on the SNRs of the beams. Now, the angular separation way doesn't really work well. So in this talk, I'll just focus on the SNR-based approach, which is the K-best heuristic. So in this case, how the idea basically here is that instead of searching over all possible beam pairs, we only search the top K beam pairs based on their SNRs. So to evaluate this heuristic, we plot the beam rank here. We plot the CDF of the beam rank of the beam pairs that resulted in the highest MIMO performance. But the rank is based on in terms of their single stream SNR amongst all the beam pairs. So as you can see, for single user MIMO, in nearly all the cases, the best performing MIMO beam was amongst the top 100 SISO beams. This means that we can limit the search to just the top 100 beam pairs and still achieve optimal performance, and the overhead reduces to 1.72 ms. For multi-user MIMO, on the other hand, there are some cases where if you search only within the top 100 beam pairs, you may miss some cases that will give you higher performance. And even if you do that, the overhead is close to 100 ms, which is too large. So for SU MIMO, while overhead drops significantly and you can achieve near optimal performance, for multi-user MIMO, there is a need to limit the search further. And this introduces a trade-off between how much performance you can achieve and the beam training overhead. And this depends on two parameters, the K that we've already discussed before, and how often you want to do beam training, that is the beam training period. So to evaluate this trade-off, we plot here for 3x3 multi-user MIMO. On the x-axis, we plot for different beam training periods from 10 ms all the way to 100 seconds. And for different Ks, we plot how much the achieved physical data rate can be. And we plot this for the 25th, 50th, and 75th percentile across our entire data set. So as you can see here, firstly, in the 25th percentile case, when K is 10, that means you're only searching in the top 10 beam pairs. The performance drop is more than 3 Gbps in the 25th percentile case. On the other hand, if you have a larger K, where you are searching in the 50 or 100 beam pairs, the beam training overhead becomes too high. So if you see for the lower beam training periods, the performance drop is significant in all the cases. Now, K20, on the other hand, basically strikes a good balance, and it only, while only inducing overhead of 1.13 ms. So finally, we look at the group selection aspect of multi-user MIMO. So we've already talked about the beam selection overhead, but in multi-user MIMO, there's another thing, which is the group selection, and the overhead of that is also critical to MIMO performance. Taking into account these overheads, we propose two heuristics to guarantee an improvement in performance when performing multi-user MIMO over single stream communication. We further compare them against two heuristics from previous work, the I2PM heuristics, which partitions users into M partitions based on their SISO SNRs, where M is the number of the streams of communication, and forms groups incrementally, picking one user from each partition, and exhaustively coupled, which tests all possible user groups to find the best one. We also compare our heuristics against an Oracle solution, which always performs optimally. So our two heuristics, SNR and RSNR-B, how they work is that for each user, they first check if that user is above the SNR thresholds that we defined earlier. And if that is the case, with that user, we form a group by finding other users which have the closest single stream SNR to that user. And once we found the group, we perform beam selection for that group using the K-best approach. Now, how these two differ is that RSNR-B has an additional step. And this additional step is that after the first round of group selection is complete, in every subsequent round, it will try a random new group with different users to see if it can achieve better performance. So to evaluate this, what we did was for all the 4 environments that we have, we calculated the aggregate throughput that can be achieved with all the heuristics by varying the number of users. Now, the key thing to note here is that irrespective of the environments and the number of users, our two heuristics, SNR-B and RSNR-B, achieve the highest MIMO aggregate performance amongst all the heuristics and achieve close to 80% of what the Oracle can provide. This shows that the RSNRB and SNRB's group selection algorithms work well across environments and even across different number of users. And they also keep the beam selection overhead low. So looking at the channel utilization, SNRB and RSNRB have lower utilization than I2PM, but they still perform better, as we saw in the previous slide, because of their better beam and group selection techniques. Between the two, SNRB and RSNRB, again, RSNRB has lower channel utilization than SNRB because it tries a random new group in every subsequent round, but it offsets that overhead with better performance from these new groups. So in conclusion, we conducted the first large-scale experimental evaluation of single-user and multi-user MIMO in 60 GHz wireless LANs. We explored whether it's possible to decide when to enable MIMO. We performed a detailed study of the overhead performance trade-off of beam and user selection. And we proposed heuristics that perform user and beam selection with low overhead. And we finally showed that they perform close to an Oracle solution and outperform previously proposed approaches. Thank you.